Alright, so yeah, as I mentioned, we can restart from where we left last time. Can anyone remind me what we talked about last time, please? You can look at your notes. Do you have notes from last time? Okay, okay. And this is what we did. Thank you very much. So last time we kept working on damped systems, and in particular we looked at we started from the general solution of the can you see my screen now? Yeah, okay. So we started with the general solution of the second order differential equation that describes the behavior of a damped single degree of freedom system. So, and we said, okay, even in this case we have to find the particular solution, which means we have to find basically A and phi as a function of the properties, the parameters of the system. So in order to find A and phi, also in this case, we need to apply the initial conditions, which means that you have to apply the initial position condition and the initial velocity condition. A lot of algebraic steps at this point, and then finally we can find the expression of A and phi for so amplitude and phase for a damped single degree of freedom system. So again, this is a particular solution. We also rewrote the equation of motion in the standard form. So it means that we rewrote the equation of motion by using the definition of the damping ratio, and also from the natural frequency that we knew from the undamped systems. And then we went through a couple of problems. In the first case, we had a system and we knew the value of the elastic constant, the mass, and the constant of the dashpot, and we were asked to calculate the natural frequency, we were asked to calculate the damping ratio, and we were asked to determine the damped natural frequency, and then also we were asked to determine if the system is underdamped, critically damped, or overdamped. For these quantities, we simply applied the equations for omega n, zeta, and omega d to determine if the system is underdamped, overdamped, or critically damped. We simply need to look at the value of zeta, the damping ratio. Since it is between 0 and 1, the system is underdamped, which means that it actually oscillates. And then for problem number 2, we knew that the system has a certain natural frequency expressed in hertz. We already knew the damping ratio, and we also knew the initial velocity and initial position. So with this information we need to determine the displacement as a function of time, and also we have to determine the maximum amplitude if we have no damping. Even in this case, pretty straightforward. For the part, let's say part A of the problem, so finding x of t, we can simply recall the solution of the equation of motion. Remember, this is valid every time we work with a single degree damped system, underdamped system. So we have A and phi. We just simply need to calculate all our quantities, omega n, omega d. We plug in the expression of A and phi so that we can find our x of t. So the displacement is a function of time. This is the expression that we were searching for. For the second part, we were asked to determine the maximum amplitude when c is equal to 0. So this was like an important detail. because when C is equal to 0, it means that basically we go back to the previous condition, which means it's an undamped system. If C is equal to 0, it means we don't have any damping at all. If C is equal to 0, we don't have damping. We can recall the same expressions that we found before for the amplitude and the phase. In this case, we were asked to find only the amplitude, so we can look at the amplitude, or we can simply take the expression that we found for the damped system and plug zeta equal to 0. Because in this case, again, the system is undamped. The result will be exactly the same, and this actually let us understand that the undamped system is simply a particular case of damped systems where zeta or C are equal to 0. Make sense? Any question about what we did last time? Alright, if there are no questions, we can move forward. Today is 2. So today I would like to talk a little bit more about springs in series and in parallel. So at this point we should be familiar with how springs in series and in parallel look like, but we can do a little bit of derivation to see how we can deal with this type of situations when we find them. So in general, what is the difference between having springs in series and in parallel? Any idea, any suggestion? What we should... Sorry, I was saying what we should look at to determine if two or more springs are in series or in parallel. Yeah, I think for almost the entire course we will talk about the linear springs. So yes, we are talking about the linear springs. So if we know that the force is split between the two, what do we really need to look at to determine if the two springs are in parallel? So in one case we need to look at the force, and in the other case we need to look at the displacement. In particular, if we have two springs that are in parallel, it means that they are subjected to the same displacement, which could be the same elongation or the same contraction. When we look at springs that are in series, they are actually subjected to the same force, but they can have different displacement. So now that we know this piece of information, we can do a little bit of calculation and find equations that will let us, generalize the situations of springs in series and in parallel. So let's start with a system that looks like this. So of course we have a certain spring K1, another spring K2, and then we also have a certain mass M. So in this case, the springs are subjected to the same force because they are basically, let's say, consecutive springs, which means that the force that comes, in this case, from the weight of the mass is applied in the same way to both springs. So that's why in this case we can talk about springs in series. So when we go back to the equation that define every single spring, we can write the following. We can write that delta 1, which is the displacement of the first spring, is equal to the weight, we indicate the force with W, which is the weight of the mass, divided by K1. Same thing for the other spring, we can write that delta 2 is also equal to W, again subject to the same force, divided by K2. Now, if you look at the geometry of the system here, we have the two springs that are, again, let's say consecutive springs, which means that we can actually calculate the total displacement as the summation of the displacement of the first one and the displacement of the second one. So from delta 1 and delta 2 we can find the total displacement, so delta total, which will be equal to delta 1 plus delta 2. Of course we can plug this quantity, so we'll have W over K1 plus W over K2. Make sense? Now, the goal in this case is to find the equivalent elastic constant of these two springs together. So if we consider that these two springs are like, let's say, a single block, we can introduce again the equivalent elastic constant. So we'll have that the force is equal to K equivalent times the, so the K equivalent multiplied by the total displacement, which means that we can obtain from here the expression of K equivalent, which is equal to the weight divided by the total displacement. We found the expression of the total displacement from here, so basically we can plug, so we have W over K1 plus W over K2. Of course here we can simplify the weight W, so we have that K equivalent will be equal to 1 divided by 1 over K1 plus 1 over K2. So this expression here is the one that we found when we have two springs in series, but of course we can extend this to whatever number we want for springs. So we can write the general expression as, so K equivalent will be equal to 1 divided by summation for I that goes between 1 and n of 1 over Ki. So from now on, every time we have n springs in series, of course we don't need to go through all these calculations, we can just apply this formula here. Make sense? Any question about these steps? This step here. Okay, so the goal of all this procedure is to find an equivalent spring to whatever system of springs we have. So if you consider that these two springs are like within a box, so you don't know exactly what's inside, but you know that they somehow have a certain elastic constant, like all together. So you can consider these two as like a single block, of springs, and you know that that single block will have a certain elastic constant. So you know that this block is subjected to a certain weight, which is the force at which it is subjected, and it is because of this force we have a certain displacement of the entire block. So this is the concept behind this one. So we have that the equivalent stiffness of the spring multiplied by the total displacement must be equal to the force, because this is how we usually describe springs. Now from here, sorry, this is like a scrap. So from here we found that the total displacement from this equation. We can plug, we can rearrange, and we can find the expression of the equivalent stiffness. Make sense? Let's look at the other case now. So the other case would be something that looks like this. Even in this case we have K1, K2 and M. So what do we have here? We have springs in series or in parallel. Yes. In this case, we are looking at springs that are in parallel, even if they seem like consecutive because they are kind of aligned, but we have to be careful. In this case, we talk about springs in series because they are subjected to the same displacement. If the mass goes up by a certain quantity, the top spring is squeezed by a certain amount, and the bottom spring is extended by the exact same amount. Same thing if the mass goes down, it means the top spring is stretched by a certain amount, the bottom spring is compressed by the exact same amount. So in this case we are talking about springs that are in parallel. Even in this case, we can do the same thing. We can try to find an expression for an equivalent spring that can replace these two springs here. Again, in this case, we know that they are subjected to the same displacement, not the same force. But we know that the force of the total force from the first spring and the second spring must balance the force that comes from the mass itself. Which means that mathematically we can write something like this. We can write F1, which is the force of the first spring, plus F2 must be equal to the force, in this case the force of gravity, which is like W. Like we did before, we can write an expression for each spring, which means that we have F1 will be equal to K1 delta 1, and F2 is equal to K2 times delta 2. So we can plug this here and this here. So what we obtain is K1 delta 1 plus K2 delta 2 equal to W. By definition, we said that the displacement must be the same for the two springs, so we can drop here the subscript, so we'll have K1 delta plus K2 delta is equal to W. So we'll have K1 plus K2 delta equal to W. Which means that we already found the expression of the equivalent spring, of the equivalent stiffness. So again, this is valid for a situation where we have two springs. We can extend for as many as we want, so we can have that K equivalent will be simply the summation up to n, again, n springs of ki. Any question? Alright, let's see a quick application of these concepts here. So we will have a system that looks like this. So here we have K1, and then we have K2, and then we have K3, and then we have K4, and then we have K5. So what we have to do in this case, we have to find the natural frequency. Alright, I would like you to spend a few minutes on this, and we can find the natural frequency of this system here.